Hello everyone, in this video we are going to see the state space model of buck-boost converter. We all know that the buck-boost converter is a DC to DC converter whose output voltage is lesser or greater than the input voltage. The circuit of the buck-boost converter is shown here, which has a switch, a diode, inductor and capacitor. Now we are going to see the state space model. It is a mathematical model of any physical system which relates the input, output and the state variables. The state space model are given by a set of first-order differential equations. The state variables are the set of variables which are used to describe the dynamics of the system. The output variables and its values depends on state variables. The advantage of state space model is that it can be applied to any type of system such as linear, nonlinear, time variant, time invariant, single input and multi-input and multi-output system. The state space model of any system consists of two equations, state equation and the output equation. The state equation is given by x dot equal to ax plus bu. The output equation is given by y is equal to cx plus du, where x is the state vector, x dot is the derivative of the state vector, y is the output vector, u is the input vector, A is the state transition matrix, B is the input matrix, C is the output matrix, D is the feed-forward matrix. Now we are going to write the state equation and the output equation for buck-boost converter. During mode 1, switch S is in the on condition and diode is in the off condition. Writing the voltage and the current equation of the capacitor, we get VL equal to L into the IL by dt equal to Vs by applying KVL here, from which we can write the IL by dt equal to 1 by L into Vs. And similarly, the current flowing through the capacitor can be written as IC is equal to C into dVC by dt equal to I naught, where I naught is nothing but V naught by R. Substituting V naught equal to minus Vc, we get dVc by dt equal to minus Vc by RC. And these two are nothing but the state equations which can be written in the matrix form to get the state equation during mode 1. So the output equation is nothing but V naught equal to minus Vc. So writing this again in the matrix form, we get y is equal to 0 minus 1 IL Vc. So this is the state equation and this is the output equation for mode 1. The matrix A1 is this one, 0, 0, 0 minus 1 by RC. This is the state vector which has the current through the inductor and the voltage across the capacitor. And then V1 vector is 1 by L0. And this is the C1 row vector. Similarly, for mode 2, we can obtain the dIL by dt and dVc by dt. During mode 2, switch S is in the off condition and diode will be in the on condition. So writing the voltage across the inductor, L into dIL by dt can be written as equal to V naught. So from which we can write dIL by dt equal to minus 1 by L into Vc, where V naught is nothing but minus Vc. And applying KCL at this node, we can write that IC plus I naught equal to IL, or IC is equal to IL minus I naught. IC can be written as C into dVc by dt. And so we can write C into dVc by dt equal to IL minus I naught. That is equal to IL minus V naught by R, which gives dVc by dt equal to IL by C plus Vc by RC, where V naught is minus Vc. And again, the output equation V naught equal to minus Vc. Writing all these equations in the matrix form, we get the state equation in matrix form and the output equation in matrix form for mode 2. So here this is A2 matrix and this is B2 matrix, this is C2 matrix. Now we have obtained the state equation and the output equation for mode 1 and mode 2 separately. But in order to have the combined state space model, we have to go for the average state space model, which combines both on and the off conditions of the entire model. So for that, we need to do this average state space model. Average state space model we have to do the approximation. To get the average state space model, we have to do the approximation of the converter as a continuous linear system. So it requires that the effective corner frequency of the output filter can be much smaller than the switching frequency. So in order to get the average state space model, we have to do the continuous linear, we have to approximate the converter as a continuous linear system. So to get the average state space model, we need to have this condition, That is x dot equal to, we have to combine both the state equations. So x dot equal to a1x plus b1u into k plus a2x plus b2u into 1 minus k. Similarly, the overall overall output equation for the average state space model is c1xk plus c2x into 1 minus k. Now we all know, we have already derived a1, b1, a2, b2, c1, c2, and all. So to get the average state space model, we have to substitute the values of a1 and a2, and finally we have to find the final version of the state space model, which is nothing but the average state space model. So A can be written as a1k plus a2 into 1 minus k, B can be written as b1k plus b2 into 1 minus k, and C can be written as c1k plus c2 into 1 minus k. Substituting A1, A2, B1, B2, C1, C2, we get the average state space model of the buck-boost converter as given by the following two equations. The first equation is the state equation, which is nothing but IL dot VC dot equal to 0, K minus 1 by L, 1 minus K by C, 1 minus 2K by RC into IL VC plus K by L 0 into Vs. The output equation is V naught equal to 0 minus 1 into IL VC. So this is the A matrix, this is B vector, this is C vector. So far we have derived the state space model for mode 1 and mode 2, and we have combined the model for on and the on period to get the average state space model, which is the required state space model of the buck-boost converter. Thank you.